Can you hear me, Fong?
I can hear you, yeah.
All right, perfect. I've already sent out an email with all of your information to the whole club, so everybody should have a background on you, and we should be prepared for you to go ahead and start whenever you're ready.
Yeah, it sounds good. Okay, let's see. How do I take over? How do you? See, I don't use this. I use Zoom. So if I'm showing my slide, in other words, my screen, how do I do this?
There should be a share button. I don't know.
Share. Okay. Oh, there's a share. Okay, okay, I see it. Share here. And so what do you see?
You see your desktop
Oh,
and
I see it. I got it. I see you guys. Great. Okay, it's all set. Okay, so you hear me fine?
yes.
Okay, very good. Here we go. Hey, thanks a lot. Yeah, I've never used Teams. Everyone seems to use Zoom. Is Teams, is it a freebie or do they charge?
It's free.
Oh, that's why. Okay. Zoom is not free unless you go like 40 minutes. Okay, well, thanks a lot for inviting me. So are you guys getting a heat wave where you're at?
We had it, yeah.
Oh, okay. Okay. Yeah, we've got nice weather here. It's about 80 right now, so it's fine. Okay, thanks a lot for inviting me to talk. And my name's Ed Fong. You've read. I teach over at UC Santa Cruz. I teach RF wireless. Let's see. I teach an antennas design class, graduate class, and RF wireless communications class, which is really real cool for advanced ham radio operating, all the theory and all the math. And I teach a optics class. That's all now. I don't teach any undergrad anymore. Anyway, I'm going to talk about dual band antenna. A lot of you guys may have heard of it. I'm going to just get into more details. I give a series of lectures to ham clubs from radio design, from single. It basically, and you can invite me back if you like the way how I present material. It's basically a lot of my college classes, but more without the math, right? And hams, we don't want to hear the math. If you're going to get into it, fine. But how we generate single sideband using I and Q without filters. Let's see. I give a class on history of handy talkies, the evolution of walkie-talkies. Let's see. I give one on phase lock loops. Anyway, I've converted a lot of my graduate level classes to ham radio 1 hour sessions. It's people have really enjoyed listening to. But here's an example, right? I actually teach this in my class, in my antennas class at the end. Here's a good example of one. And then you'll see I've kind of taken away all the math, more intuition, more of the fun stuff. So I'm going to talk tonight about the dual band J-pole. It's very popular. We came up with this idea about 20 years ago, published it in QST. It's also in the antenna handbook and the antenna compendium, both volumes at Antenna Classic. So it's a pretty classic design now. 20 years ago, it was pretty innovative. And I'll give you a little history behind it. And then ask questions in the end. Feel free to ask questions in the end. So, wow, I see the screen. That appears pretty quick. Okay. So here's the article on the one I'm going to talk about tonight on the right. And we did a portable version, roll up, same principles, but physically a little bit different. We'll talk about that too. We published that a few years later. And then we also make a tri-band. Now this has been a very, very popular talk. I'll be more than glad to give this talk to you folks later on too, because tri-band, very few tri-band antennas out there. I'll give you the history behind why we did it. We did it for FEMA mainly. They wanted us to develop a 2-meter 224/40 antenna with all these interesting requirements, and we met them for a good price. The club members get it for like $60, so you can't beat it. That's my daughter there, KJ6QXM. She's a mechanical engineer, master's in mechanical, and also master's in robotics. She works at Abbott Labs on non-invasive valve replacements. Really cool stuff. Okay, and the one I'm going to talk about tonight, not patented. And you said, why did you patent this? It's a cool idea. I just didn't know. This is 20 years ago. I figured it was a ham project. We published it, it worked. The only reason that I just didn't think about patenting it. And the reason why we did afterwards, people started copying the design I'm going to present tonight. People initially were copying it, were selling it. Amazing. They were even selling it as buy the Ed Fong antenna from us. And we did. Some of my students, I couldn't buy it because they would know it was me, but some of my students did. And they were lousy. It's very tricky to build one of these. The principles are there. To get the right materials, exactly the right dimensions, That's the critical part. It's like what my friend used to say, it's the details that make this work. But I'll go through those details, and you'll see that the materials are all special ordered. We don't order anything online. Everything has to be special ordered for consistency. So subsequently, we patented our other antennas, even though we developed them at the university, they're ham stuff. Our attorney, Mike Kaufman, who's CVD, K6 CVD, I think it's called. He works a lot of DX. He's a good guy. He loves that patent ham stuff because he's a ham. So he patented this, our collinear gain antenna technique, and also our tri-band 2-meter 224/40. You may have read that in QST. It's a very clever design. Wow, it really sells well these days. It's really caught on, especially as 220 caught on. A lot of folks, instead of buying the dual band one that I presented today, they just, well, at $20, I'll take the tri-band. Why not? Then they'll get on 220. And then this interesting way of achieving gain, not that simple, to get about 5 dB of gain. That was, who requested? Oh, I know, ATD Alarms gave us a grant. That was from a grant. That was a grant from ATD Alarms. But most of these I just developed because they're fun. But yeah, that one was from a grant from ATD. I have a talk on that. So I give a lot of talks. If you guys, Justin, I know how it is. I am one of the people that gets the monthly talks for our 2 clubs. And I know how it is. After a while, you run out of people to go to. And then I end up speaking. That's why I have those other lectures. Okay, I'll come up with something. I'll take some of my lecture notes, some slides, convert it to a ham talk. Usually it turns out okay. I just take out all the math. Okay, so let's get to tonight's talk. Why a J-pole? The J-pole, when I was growing up back in the 60s, we just knew about ground planes. You built a ground plane out of an SL239 flipped, put some number one with 16 or 14 wire, put 3 radios on it. You measure the SWR, and it's fine. It works. I'm 13 years old. What do I know, right? You measure the SWR. People say measure the SWR. I thought you measure the SWR. If it's low, it must be good. Well, it's necessary, but not sufficient. That's what a mathematician would call it. Yes, you need a good SWR, but that doesn't mean you have a good antenna. The good antenna is much more complicated to measure. You got to measure the radiation patterns and gains and all that stuff. So when I looked into this back in the early 2000s, found out that the J-pole, I started building J-poles because it got popular to swamp me. People say, hey, you got to try the J-pole thing. It doesn't need a lightning arrestor. It doesn't have radials. Okay, I'll try it. I tried it. It does work. And it does work, not significantly better than a ground plane, but it's better. It's definitely noticeably better. I mean, it's not like night and day, but it's basically when you quantify, it's about 1.6 dB. If you use a J-pole antenna, it should perform about 1.6 dB better than a ground plane. It's more ideal, close to an ideal pattern. A ground plane does not have that low angle radiation. It's okay until you use a J-pole. J-pole has a lower angle radiation, giving you about 1.5 dB of gain at the horizon. That's because it's vertical height. I'll show you why in a while. See, it's interesting. I took this picture a few years ago. If you're familiar with San Francisco, this is on Sutro Tower. This is the commercial antenna on Sutro Tower. Police, fire, ambulance. I don't know who's up here. That's a commercial transmitter of some kind. I took the picture because I was up there with my daughter. She was into photography, and I said, let's go take some pictures up at Twin Peaks, look at the clouds, the fog rolling in. So I bring it home, I downloaded it, and I go, wow, this is interesting. Here's a bunch of antennas. You notice there's not a single one with radials? Either they've all fallen off, or else they've all changed to the design I'm going to discuss today, a J-pole type design, right? There are no radials in any of these. Because the thing about radials, you can't have something horizontal. Like I'm not on camera anymore here, showing my slide. That's okay. If you hold something horizontally, you can't hold it up. If I hold up an antenna vertically on my hand, I can hold it up easily like this. But if you slip this horizontal, they take the antenna, put it horizontal, that would fall off in the season because of the horizontal force. So horizontal forces are not good, like radials. They will fall off. They'll just havoc problems. Well, with a J-pole configuration, everything's all vertical. It's all vertical, nothing sticking out. It works not only just as well, it works about 1.6 dB better. Now, you say, well, what's the trade-off? The trade-off is it's 3 1/4 wavelengths tall, right? A ground plane is 1/4 wavelength with 3 radios, which are a quarter wavelength also. In a J-pole, it's 3 1/4 wavelengths tall. So that's 3 times taller than a ground plane. But it has no radios and does not need a lightning arrestor. So let me show you this in a while. See, here's an antenna I built for a repeater years ago. I took this picture years ago. In fact, this wasn't even digital. This was originally on film. I scanned it. I don't know how you guys are, but when you're young, you're a teenager, 1967, repeaters were the in thing. Everyone's building repeaters. I'm willing to build anything they tell me to build. I'm going to all the ham club meetings I can go to, you know, that my bus can take me to, and then my folks would drive me to ham meetings every night. There were so many ham clubs I can go to, you know, that, and I was more than willing to volunteer. And my dad, my folks, would, yeah, help them out. They didn't know what was going on, but I would build these copper J-pole. Here was a vertical dipole. Let's see, the audio, the mic is on there. I can maybe mute the mic. Okay. Anyway, here's a repeater antenna we built, and we would even phase these. So this is a standard dipole. You know, it's 90 degrees fed because this is the top and this is the bottom. Well, this is a dipole antenna. It's great, but there's another thing about antennas. Just you can design an antenna that resonates. That's one. So it has to work electronically, but it also has to be compatible physically where you're going to place it. So 2 things. First of all, it's got to resonate, sure. But then is it a practical physical design? This is not a practical physical design. Let me tell you why. Here's the thing holding it up. Well, that's not good. That's too close. It's going to act as a reflector, always, a little bit of reflection. It may not affect the SWR if it's far out enough, but it certainly will affect the pattern. Let me guarantee you, it will affect the pattern. It will act as some kind of a reflector and bias the signal towards this direction. So that's not good. It's not omnidirectional. You got to feed it 90 degrees. That's not good. If you got to feed it 90 degrees, that means you got to put it out on the arm. And the further you put this out, the more that resembles free space. Great. Electromagnetically, but not physically. Mechanically, it's terrible because you're going to torque that node right there. Right, my daughter, who's a mechanical engineer, will call that R cross F force. The further you put this out, the more torque you're going to put over there. It's R cross F. This is the distance times the force. Whatever force you have to multiply by the distance. More distance, you get a multiplication. And so, you know, if this is only about a foot, it's okay. This eventually broke very quickly on a hill, by the way. What happens is this. Again, electromagnetically, it's fine, but physically, it's not. What happens is this is all solder. Solder is very, very soft. I mean, if the thing is not moving, you're okay. You know, like you solder a resistor in a board, it's not moving. That's okay. But as you know, you get a piece of solder, you know how soft it is. It's not steel. It's not iron. It's not titanium. It's solder. Very soft, basically soft as butter. So what happens is you can't use that reliably on an antenna that's on the air that all winter will be, you know, blowing winds, 100 miles an hour, going back and forth, cracks very quickly. So this goes to show you, although this antenna is electromagnetically okay, it's a good example of something physically not okay, not okay at all. So that's why you see all this. They've come, you know, when you have to climb a tower like this, you know, it's not like my backyard. I decide, wake up in the morning and say, oh, that's right, I got to go adjust that antenna. It's only up to me. I fall off the tower, my wife doesn't care. I call it 911. Right? But here, when they climb, you know, I've been involved in these things. I do antennas. I do commercially. We do a lot of consulting. I know what it takes. They don't let me climb that. I don't mind climbing. That'd be fun. They won't let me climb. You got to be certified climber. You got to get a permit for a tower like this. You got to prepare all the things because it's windy up there. All the things you got to do. You got to have all the tools you want climbing up and down. It's pretty dangerous. So you need a city plan, you need a permit, and you need a team and a safety team. You're talking minimum, not even in the antenna. Minimum planning $1,000. So you want an antenna that lasts. You don't want one of the ground radios. 1 year later, you pull out your binoculars. Oh, that radio fell off. Not worth $1,000 going up there replacing it. You got to just get one. No radios. That's what they do. No radios. So that's why I like this J-pole design. We'll get into it in details because no radios, and it does not require a lightning arrestor. We'll show you that. It's a DC shorted design. So, when you start putting lightning arresters and antennas, I've noticed at UHF and above, it's very hard or very expensive to get one that you can put in line, does not change the impedance. The losses are 0.1, 0.2 dB. You can do. They all kind of change something to impedes because of the connectors. So if you don't need one, all that much better. Okay. So let's go back to this J-pole. I first saw this J-pole, it was in the maybe late 1990s. My friend Danny Monticelli introduced me. I didn't know anything about him at that time, even though I was teaching. I had heard about it, but that was it. He showed me, hey, take one of these. He just built it out of ribbon cable from Radio Shack. And he said, what deal? $3 back then, 50 feet, you could build, you could build 15 of them for $3. Took it home, tried it out. I said, Denny, you're right. This thing, I didn't measure it, but I said, this is better than the ground plane. Yeah, you can tell. 1.5 dB, it's not significant, but you can tell. Yeah, it is better. And so I really was attracted to it. No radios. It's a DC short circuit. I got to experiment with it more. I looked at it, I said, what we just should do is stick that little ribbon J into a PVC pipe, seal it, make it a base station antenna. And we did. Single band, but of course, the demand was a dual band. That's what we're going to get in today. Let's see. Let's go into the actual J-pole. See, here's a 2-meter J-pole. Probably a lot of you guys have built this. So, I've got some things to show. I'm seeing, Justin, can you view, and this, can you show my room, my camera, instead of my slide?
We're seeing your camera right now, like in the top.
No, you should be seeing my face. Oh,
We do.
Yeah.
oh, can you see me? I'm not sure. Hang on.
Yes.
Oh, you can see me wave my hands.
Yes.
Yes. Okay. Okay. Oh, good. Okay. I see. Okay. You can see me. Okay. Very good. So here's the typical J-pole, and a lot of people have built these. They're really handy. You make it out of twin lead, and basically this is how it works, right? The half wave antenna's here, 37, 38 inches half wave. And in a half wave dipole, you would have fed it in the middle, right? So if it was truly a half wave, you would have fed it in the middle because it's 60 ohms or so. You can feed it with coax at 90 degrees, but hope I've convinced you that's not the best way to do it. Physically, it will work for a while, but this is going to break. See, I was going to show you this example now that I can see myself. Here. See, us antenna designers, practical antenna designers, I can hold up one of our J-poles in a PVC pipe like this. It's vertical. This thing only weighs about 12 ounces. I don't feel a thing. I mean, I can hold this pretty long, but I can't, if I had it horizontal, I can't hold it very long. I can't do this. No way. It falls right off because it's got R cross F force or horizontal force. That's why this is not good physically. It just won't last long. So in a J-pole, you can feed it from the bottom, but how do you feed it from the bottom? That was the problem that was solved. If this is half wave, it's about 60 ohms or so matchable in the middle. But then you have to tap it off. At the ends of a dipole is high impedance, low current. In the middle, it's high current, low voltage. So it's lower impedance. So the trick is, how do you match it to this point? Because if you could, then you can put a quarter wave stub here. This is how you do it. You take a quarter wave stub because you need to match a high impedance. How do you get high impedance out of 50 ohms? You look at a Smith chart here. You look at a Smith chart and you say a Smith chart says short circuit transmission line, a short circuit now. It doesn't matter whether it's 300 ohms, 50 ohms, 75 ohms. If you take a short circuit on one end, if you move 1/4 wavelength within that transmission line, 1/4 wavelength within that transmission line. So twin lead, 15, 16 inches is going to be a quarter wave. Coax, a little lower, it'll be about 14 inches. Within that coax, that would be a quarter wave at 2 meters. So let's go back to this here. So you take a twin lead, for example, short circuit the bottom, DC short. You move up. If you move up about 16.5 inches, 15 and a quarter plus 1 1/4, according to the Smith chart, that would be high impedance. And you can look at it this way. If this is a short circuit, it's going to be 0 ohms, obviously. As you drive this wave, as you move up a quarter wavelength, you get a maximum voltage. It'll be a quarter wave, right? Because it's a sine wave. It's 0 here. A quarter wave at 2 meters, about 16 inches up, will be a peak voltage. Well, if it's a peak voltage, it's got to be low current because you're not creating power. It's Ohm's law. The power stays constant, which says it's high impedance. That's another way of looking at it. Smith chart shows you this exact same thing. Short circuit to a quarter wave, it's going to be high impedance. In case of 2 meters, about 16, 17 inches. In the case of UHF, only about 5 inches. And an interesting question comes about. If this is a quarter wave, isn't a quarter wave more like 18 inches or 2 meters? That's an air, not in twin lead. In twin lead, the speed of light slows down by 15, 20%. Where this dimension comes from, where you get 18 inches, it comes from a very basic formula. C equals F lambda. The speed of light is always equal to the frequency times the wavelength. You had that in your extra class exam, I know. Maybe you've forgotten it, but the speed of light is always equal to frequency times the wavelength. The difference is if you use 3 times 10 to the 8th meters a second, speed of light in air or in a vacuum, and you plug in 150 megahertz, the wavelength will be 2 meters. But in twin lead, it doesn't travel at 3 times 10 to the 8th meters a second. And that's more like 2.5 meters times 8 meters, 2.5 times 10 to the 8th meters a second. A little bit slower, which means if you put in the frequency for 2 meters, the lambda 2 meter wavelength in twin lead is not about 18 inches. That's an air. In a twin lead, it's about 16.5, right? 15 and a quarter plus 1 1/4, about all 16.5. It's a little bit shorter. So that's why the discrepancy in the lengths. But basically what you've done here is you start out as a short circuit and you go up a transmission line, quarter wavelength, in the case of 2 meters, to about 16.5 inches. It's a high impedance. Well, that matches the end of the high impedance of the dipole. So it matches right into it. And then you can say, well, if that's 0 ohms, and that's, maybe not infinity, very high impedance, several thousand ohms, got to be 50 ohms or close to 50 ohms somewhere. It turns out there is about 1 1/4 inch, depending on the material. And that's where you match it. See, so here's where the DC short comes in. You tap it off to coax, RG174 or 8X or whatever you want. And again, what happens, this is 0 ohms, that's high impedance. About 1 1/4 inch, you get 50 ohms, and then you match. Now, the advantage here is, yeah, it's tall. You know, this is it's a 1/2 wavelength here and 1/4 wavelength there. Because a ground plane would have been about this tall, but radials, but it would have been open circuit. So this is a DC short. So you don't need a lightning arrestor. You put an ohmmeter across that DC, it's a short circuit. Now, it is not a short circuit, obviously, at VHF. Its impedance is about 50 ohms because it's resonating. And it also is a 50 ohm impedance at about UHF in that range. So that's why it works. Why does it have a better pattern? Lower angle radiation. Again, without the math, this is why. In a normal ground plane, you have a quarter wave going up, or let's say a quarter wave going up, you have ground radials. The ground radials are not 180 degrees, they're 90 degrees or whatever. It doesn't push the wave down low enough angle because the radials are at 90 degrees or maybe a little bit more, but still, it's not optimum. Here it's 180 degrees, quarter wave up to quarter wave down. What's pulling and making a figure 8 pattern really symmetric is this other quarter wave pulling it down. Is this significant? It's about 1.5 dB significant. Not major, but you could notice it. You notice it. It's clearly measurable, and you'll notice it, but it's 1.5 dB is 1.5 dB. Better than nothing. So that is how basically the J-pole works over a dipole like this. So you put it in a PVC pipe, great. Okay, so how do you make this dual band? That's just VHF. Well, it's interesting. So in the 2000 era, getting all these HROs is selling you dual band handy talkies, dual band mobiles, convincing and perhaps right. You're going to come in and buy a new radio? I know you've been operating 2 meters, but all these UHF repeaters are coming. You know, basically for an extra $50, you get a dual band Alinco or Yaesu or ICOM or whatever. And they said, well, sounds good. I'll pay you extra $50 and get the extra UHF. Except, kind of like going to the dentist, right? The checkup's free, but then you need all this to work. Basically, $50 will give you another band. Don't you need an antenna? And that's where HROs, you know, made quite a bit of money on that. A dual band antenna, you would have to buy a new dual band antenna. And, you know, you go to a Comet or Diamond, they're not cheap. You say it's a good one, $200. So they made their money. But, you know, hams, I don't know. I'm sure the culture is no different back there than we are here. We don't want to spend money unless it's for a really good value. So a lot of these guys bought their radios and they needed an antenna. They did, you know, they were spending $250, $300 on a radio. I didn't want to spend another $200 just to get on UHF. What they noticed was that the J-pole or the ground plane they were using would also work on UHF. Because the first thing you do is you measure the SWR. Here's a perfect example. SWR is necessary but not sufficient. They measure the SWR 1.5 to 1. Good enough. The radio is not going to blow up. But what they quickly notice, pretty good SWR, but terrible performance. That's the key. It's terrible performance. Actually, when you use a 2 meter antenna at UHF at the third harmonic, you get about a 6 to 8 dB loss. And the way it works is if you build an antenna like a dipole, for instance, these days you can confirm this very easily because everyone's got one of these nano VNAs for less than $100. Recommend this, but you don't have one, best thing around for under $100. You'll find that if you build for example, a dipole at 100 megahertz, you look at your nano VNA, wow, it dips at 300, 500, 700, etc. Because that's how antennas work. Every time you go to third harmonic, it resonates again. And the way to explain this, if you believe in the Smith chart, basically what you're saying is this. If you go around a half wavelength, well, no, that's, yes, okay. It's a quarter wavelength. You go around a quarter wavelength, and you go another quarter wavelength, which is a half wavelength. Every time you go a half wavelength more, in other words, from 2 meters to 440, it's a half wavelength more. You go back to the same spot. Resonance-wise, let's see, can I explain? I think I give another explanation. Here's a good explanation. Here's the stub. Quarter wavelength. Assume that I've already convinced you that it's short circuit, infinity, 2 meters only, and about 1 1/4 inch, you get 50 ohms. If you look at the plot of the voltage here, it's 0, and then as it goes up a quarter wavelength, it's a high voltage, which means low current, because Ohm's law is you set the same power. If it's high voltage, low current. If it's high current, it's low voltage. But up here, it's high voltage, low current at VHF. Look at what happens at UHF. Why does it also match? Here's the reason, graphically. UHF, a quarter wavelength is about 5, 6 inches. You go up here, you peak here, you're still in this transmission line. That's a quarter wave. You go up another quarter wave, you're here. That's half wave now, full half wave. You go another quarter wave, whoa, high voltage point. So if you go in every half wave you go up, you come back, it matches the impedance because it's a voltage maximum. So that's the matching. That doesn't mean you have an antenna. It means you have a matching, which kind of is deceiving because you say, oh, I go 3/4 of a wavelength, I match, I must have an antenna. You do, you have a lousy antenna. And it's resonance is necessary but not sufficient. That's because at UHF, you would like it to terminate here, go up about 12 inches, half wave, done, it'll radiate just fine. But if you leave this 37 or 38 inches, the currents go to 12 inches And it would like to see it cut off, right? You could halfway if it works, but it doesn't. The current continues up the remaining portion. And not only does it continue up the remaining portion, it continues up the wrong phase. That's not what you want. Wrong phase, that's not a good thing to learn about, because then it looks like this. Here. So here's an easy net plot, and you can do this in ADS, Spectre, RF, they'll all give you the same plot. Free space, vertical antenna, like a J-pole, okay? A ground plane antenna, this would tend to be biased up a little higher. It would be this would kind of peak up a little bit, it'll curve up. That's where you lose the 1.5 dB. But this is in free space, a true dipole. Fundamental, in this case, 2 meters, it looks like this. This is exactly what you want. This is the sky, this is sea level, and this is the earth. That's a good pattern. Now you go up to UHF, the third harmonic, it looks like this. What it says is 75% of your signal goes up into the sky and only about 25% of it remains. Remember, it still matches. The matching is not the problem, but you're spraying the energy to the wrong spot, up into the sky. So maybe this might make and actually people tell me it does work. If you want to talk to the International Space Station, this is better than a regular antenna at UHF because it's spraying it up in the sky. But put it in simple terms, another way of looking at it is your 4-watt Baofeng radio using a VHF antenna at UHF looks like a 1-watt radio. Going the wrong way, right? You want to go the other way. You want your 1-watt radio to look like a 4-watt radio, not your 4-watt radio to look like a 1-watt radio. So you got to do something about that. And again, I hope I've convinced you what's happening is the UHF is fine. It matches because it goes an extra half wavelength. So it matches up to this point. That's why you see a low SWR. You would like to see 12 inches there for half wave, but it doesn't. It sees 37. So UHF, the current continues to go out of phase. It cancels. It puts your signal up in the sky. Not good. And you'll notice it. So how do you solve this problem? Here's the copper J. Here's a single band one. Turns out I can't easily put UHF into this configuration because this does. You guys probably have copper J's. This is really popular. Same principle. Here's the half wave. You make the transmission line out of copper pipe. Here you have a T and you have an elbow. The problem with this, and it works, and I know it works because we build them. I actually build these in class as an exercise. We actually build these and we test them out. That's the only way the students have fun. You got to build them and test them out. You sit around doing all the math, you all fall asleep. And I don't know how many of you guys are engineers, but I tell you, I had so many math classes in graduate school, I don't remember a thing. And my friend Ron, who I went to graduate school with, said, Ed, do you remember any of that stuff when we went to Berkeley? I go, no. He says, why do we even learn it in the first place? I go, that's why I don't teach it. I teach the minimum amount of math. So you guys might be pretty deep, but it's actually very minimal, like how an antenna works and all the equations and things like that. But you look at this, the problem with this antenna is at VHF, and that's all they're claiming now, it's okay. Here's the half wave, and they make this transmission line, right? Here's the short, here's the tap. The problem is at UHF, this is too big, right? The jump here is about 1 7/8 inch. I measured it. That's not going to work for UHF. UHF, you're at 5 inches for a quarter wave. You can't waste 2 inches. You'll start radiating horizontally. So it's not small enough. The transmission line is not small enough for UHF. It will work because mainly you start radiating all over the place. And this transmission line, again, too wide for UHF, but marginally acceptable for VHF. VHF quarter wave, 18 inches. Yeah, so this is 2 inches. Not the greatest transmission line in the world, but it will work. Clearly, it will not work for 70 centimeters. Now, for 70 centimeters, ARRL makes a good attempt. They've got their regular J-pole, and then for UHF, they add another element. So they take the matching element for VHF as the main element for UHF and put a little 6.5 inch stub there to resonate. Yeah, it's okay. We don't build this, but I have one right here. We measured it. it's a good attempt. Definitely an improvement. Because the problem is it's got one feed line. So the UHF signal, if it's a good match, half of it goes in here, and still the other half goes in there. Of course, the part that goes in there, you lose about 25 or 75% of the energy. So at least half of it's going to the right place. So it's worth mentioning. And we have one right here too. We've tested it. Slim Jim, I don't even want to mention it. You hear about Slim Jim saying, oh, this ribbon J, you short it here, you get 6 dB gain. That's just nonsense, right? According to Dr. Larry Seebeck, he's right. It's nonsense. This is a 2-meter J-pole, and that's all it is. Okay, that's a quick review. Okay, so how did we do this? How did, after twiddling around, what did I come up with that really worked? This worked. And this idea of a shorted stub, short circuit, and quarter wave going high impedance, we use this all the time. You can make filters like this, and especially if you've got access to nanos, you can cut the coax, trim it to exactly where you want it. So what you need to do is, so at VHF, it's clear. Here's the stub, and then you got 37, 38 inches here. It works. But what do you do for UHF to stop it, for the currents from continuing? Because when they continue out of phase. So you cut it off at 11¼ inch, and at UHF, it will work fine. Of course, at VHF, if you cut it off, you don't get the rest of this piece. But again, you put a quarter wave stub there. A short circuit would be an open circuit here. But if you make it 4¼ inches, that's valid at UHF. Again, you say, isn't quarter wave 6 inches, 5, 6 inches? Not in RG174 coax. It's got a velocity factor. In fact, it travels about 25% slower than the speed of light. Actually, more than that, 0.7 around there, about 30% slower. So instead of about 5.5, 6 inches, it's about 4¼ inches. 4¼ inch, if you measure this with a nano VNA, it's a high impedance. That's what you want. At UHF, this we already convinced you this matches, but you want to see 11¼ inch here to resonate and see a high impedance there. In fact, a super high one, so you don't see this electrically. Physically, it's there, but not electrically, and that works. Because at VHF, that's not resonant anymore. It just goes right through. And sure enough, you get both bands. We've done tests on it. The ARRL has at least 2 of our samples. It works fine, exactly as promised. And like clubs have tested this out. You have a pretty clever idea, and it does work. It matches up to the X200, X50. When I heard this, we started buying a bunch of X100s and X50, having my students test it out. Yeah, this antenna works well. So what's the secret? This seems like a pretty simple antenna. I'll give you the secret to why our antennas work really, really well. One I learned from John Pertune, you guys might know, N6NBC, and Steve Stearns, K6OYK. These are really, John worked for NBC and was a microwave engineer. Steve is a Stanford guy, was the head of the electromagnetics lab at Northrop Grumman, very well known. He says, oh, when you build antennas, because they're doing microwave antennas and UHF antennas for satellites and things like that, make sure, and they're absolutely right, make sure all elements are copper, nothing else. At HF, you can get away with it, but at UHF, VHF, all copper wire, at least copper coated. Everything must be copper. What else? What else did they say? Copper, this is like number 16 wire. I think, oh, and the twin knee. The twin knee's got to be very high quality twin knee. Number 16 wire, 16 and 18 wire, pretty thick. And again, all copper, and that's true. It works. It absolutely works. Let's see what else. Okay, so this basically is a trap for the UHF. So when we measure this, here's interesting. So here are the dimensions. Goes into PVC pipe, goes into the class 200 PVC pipe. That's the thinner stuff. We find it's got a little low loss. So this velocity factor thing I keep on telling you about, like for example, when you put it in twin lead, instead of about 18 inches or quarter wavelength, it's about 16.5. That's because the speed of light in this material is going to be a little slower. It's the same thing when you plug this antenna into a PVC pipe to protect it. You have to readjust it. If you just plug it in, you'll find that you'll drop in resonant frequency by maybe 2 or 3%. So it's interesting because the roll-up version, here's the roll-up version, goes to a BNC connector. This is all one piece. I'll show it to you. It rolls up. Here. This is great to carry with you on your sodas and backpacking trips. It's the same principle, except it's all in one piece. It unravels. Here's the stub. If you see it, it's kind of camouflage. It ends up in a BNC connector, but it operates in air. It's got a little nylon tie, and you just find, you can either bring your fiberglass pole or throw a rock up in a tree and lift it up, and it works just as well, except you look at the dimensions very carefully here. This operates in air now, not in the PVC pipe. So air does have 3 times 10 to the 8th meters a second speed of light. See, now, instead of that 15 inches, that's 16 and a quarter. Instead of 17 inches, it's 18, right? So overall, when you stick this antenna into the PVC pipe to make it a base station, it's about 2 inches. 2 inches, that's not insignificant. 2 inches shorter than you would just have a roll-up. So that's a main thing to catch on to. And just the idea that we figured out how to put the stub and put a heat shrink, all get it in one piece, and it works fine. Great for portable antennas. So, and when you buy our base station antenna, make sure you put it into Lowell's 23990 PVC pipe. That's 3/4 inch thinner stuff, 200 PSI. That's what we designed it for. Of course, the roll up, no problem, just hang it in air. So you ask, does this thing work? Yeah, I think it does. How am I doing with time? Not too bad with time. Here's a reference 2-meter J-pole at UHF. Remember, it's not good at UHF because 75% of your energy is into the sky. Put that little stub, just that little stub, no changes at all, you get about 6 dB gain. That's a lot. 6 dB you will notice. 1.5 dB or so between a ground plane and a J-pole. Well, you'll notice it after a while, but it's not significant. This is significant. We're talking about your 1 watt HT looking like 4 watts and being lost. So this you will notice very quickly. And then we make these measurements. And the reason why we make these measurements is because my students love to make measurements. They want to be real engineers. The curriculum we have at our school, it's not real engineers. It's all sit-down math, right? Yeah. I'm not so sure that makes always a good engineer. At RF engineer, you guys are RF guys. You got to know how to solder. You got to know how to solder a good RF soldering contacts. That's why my grad students are all hams. And the good news is, over the years, I've converted a few. To tell you the truth, our Foothill Amateur Radio Society is about 1/3, consists of as much as 1/3 of the members are students, former students of mine that just got involved in ham radio. You got to just advertise this fact. I said there's free lectures every month. 3 or 4 times out of the year, we bring dinner. Good pizza, good Italian dinner. And they all ask, so how much does this cost? Because they're so used to paying tuition. And it's free. We're trying to recruit people. We don't charge. We can't charge. They want to come. You come to our field day. We have a great buffet dinner, and we do it at our swim and tennis club. It's free swimming. You got to entice these folks, and then you do get these folks. You do. So anyway, we made these measurements just because this guy actually made it into his master's thesis, how to actually measure performance, true measurement performance of antennas to National Institute and Standards of Technology, or NIST standards. So we actually measured it. He learned a lot about, wow, it's all, a lot of engineering is test and measurements. It's not all building and coming up. You got to build it, but you got to test it and prove it. That's where sometimes proving it is quite an effort. So here's the antenna, quarter wave mobile as a reference. And what it was just out in a parking lot on a Sunday, so you don't get people moving around. And making a measurement was like 50 yards with a spectrum analyzer and a ground plane mobile. And it was like minus 24.7 dB from a handy talkie, just relative. If we replace that antenna, the other antenna, that we're moving to a rubber duck, yeah, you do lose about 6 dB. It's true, you do. Maybe not, but around 6 dB. So rubber duck and VHF you should only use for repeater, close range. It's not a very high performance antenna. It's really for just convenience. If you go to a standard J-pole, it's like a quarter wave mobile, maybe it's a little bit better, right? Minus 23, G4 as opposed to 24.7. So not major, but if you move around and listen carefully, the J-pole will perform a little better than a quarter wave mobile or ground plane. Not significant, but I do notice it. Especially the signals are weak. You'll notice it more when the signals are weak. Then our dual band J-pole, about the same as a regular standard J-pole. And by the way they make these measurements, it turns out you need at least 5 measurements of each. According to National Institute of Standards and Technology, you're going to measure an antenna, make sure you measure a rainy day, a foggy day, and a clear day. And each of those days, they want at least 5 measurements. They don't have exact rules, but they have good recommendations. You want 5 measurements because things really vary from day to day. You have to take averages. So this shows that our J-pole is not like a regular J-pole at VHF, and a little bit better than the ground plane. So let's go to the UHF. Uh-oh. I got a phone call. Yes, yes? Yeah. Yeah, yeah. Okay. Okay, I'm giving a seminar right now. Okay, bye. Oh, it's my wife coming home from work. Okay, so how about at UHF? That's where we want to see the gain, right? It's when you use a standard VHF antenna at UHF, you get that 6 dB of loss, 75% energy loss. So again, you do a reference measurement, same situation, but it's about minus 38.8 dB as a reference. This is just with a spectrum analyzer and a signal generator, 50 yards and a fairly empty lot. And you use a UHF rubber duck. This was just with a Baofeng, so it loses a little bit, about 3 dB. About half the loss of VHF because that rubber duck's like 5 inches, and that's pretty close to a quarter wave. And what's the other quarter wave is the chassis of the Baofeng, and that is 3-4 inches, not quite a quarter wave, so there's a little bit of loss. And in some of these bigger Motorola HTs, you measure about the same, very close to that of a quarter wave because they're nice and big. Now the problem is you use the standard J-pole, then it's terrible. Yes, again, you lose about 6 dB. A standard VHF J-pole used at UHF is not the thing to do. About 6 dB of loss. The question is when you add that little stub in, that it almost all comes back. It's minus 45, and that's about minus 39. That's about 6 dB coming back at you. Just that little stub at the right spot. So it does work. Here's the original lab that we tested this, 2008. We've got a new network analyzer now. This is the 5062. I guess it's kind of old now. This is 2021. And that's my Nano. The Nano's, I mean, for $80, $90, get a Nano. The learning curve is kind of hard. I guess you guys can do some classes on it or something. The learning curve is kind of hard, but I wonder about that stub a lot. How ideal of an open circuit is it? It's not perfect. I wasn't expecting it to be perfect. You need a cavity to be perfect, but it's high, right? It's actually right there. It's pretty high. It's not infinity. That's very tough to get infinity, just like it's very tough to get 0 ohms. You get close to it. You get close to it. But I wouldn't expect a quarter wave RG174 to be up to infinity. If it was that, I can make cavities and make duplex repeaters out of coax, and you can't. It's too lossy for that, but it's better than nothing. And I was wondering about the resonance of it. When I put my hand around it, is that spot still good? Yeah, it's still pretty good. So it acts as a pretty good open circuit. See, here again, I hang this up in my house, and it's been up there for years. No problems with it because it's only a vertical force. If I had this thing horizontal, one good winter storm, it's gone. Here's a roll-up we have. Same theory that I presented here, but we include a 6-foot extension, custom made for us, male and female, so you can just add these because you can throw it up on the roof. the antenna itself's got about 3 feet built in, and we throw in all the adapters with it. So why do I give you this talk? Because this is how we raise funds. You're seeing in this room our little lab here that, in fact, the student just left. They come here and they get to experience building antennas, and I pay them. That's how we raise funds for this. Basically, their research assistantship or TA-ship. That's their substitute. They do both sometimes. What we don't have is I don't have grants anymore. Grants are just too unstable. They come and they go. I know with now, we got all our federal grants just put on hold. We might get it back, but they're on hold. We're basically $81 million this year in debt, by the way. We didn't get any federal funding. That might come back, who knows, because it's all in court, but the point is we don't have it now. So I like this idea where we raise our funds, we work for it here, we split up all the proceeds, and I get to put 2 to 3 students together of tuition and room and board and everything, 2 to 3, depending on the year. So I'm begging you to support us. That's how we support it. They build these antennas, and we build hundreds, and we sell them to hams. We also build commercial ones to spec, and we'll sell the dual band ones. We'll do custom antennas, and we'll do up to tri-band. So like this talk. So here's a talk on how you actually get gain out of a J-pole. Because again, I like the J-pole, vertical, DC short. Okay, so how do you get gain out of this thing? I'll show you how to get gain out of it. And then I have another good talk that's popular. How do you get the third band 220 out of it? Here's a tricky one that we worked on for FEMA. And I don't know how many of you guys have one. Very popular. Not too large. It's about 6.5 feet tall, all in the PVC pipe, fully enclosed. We came up with this almost 10 years ago. FEMA requested it because they were buying the Comet and Diamond ones, and they were very, very expensive. Plus, they use ground radios. This one has no radios, doesn't need a lightning arrestor, and performs fairly well. So I've given a talk on that. This is nothing. We don't. I just shows a slide of tri-band radios. We give these away at our monthly meetings. You know, if you guys are curious about trying to B-Tech ones and radio audio, we've given them away. I gotta admit, for $100, they're not bad. I'm amazed they could do it. They're probably not as good as an ICOM or Yaesu, but they're for $100, they're not bad. They put out the full power. Another talk on QRP radios. This is a radio put up together by the Northern California QRP Club. We build these in our lab in my radio communications class because I have to teach them how we develop single sideband and IQ modulation, because that's from OFDM. This can do OFDM. We buy the boards already built. They do the coils and we put them together. Mainly it's to them the settings of I and Q, the phasing. I teach them that because that's what they'll do in the industry. So I give a talk on this radio. It's a really cool radio, 80 through 10 meters, all mode, even digital cat mode. Has a CW decoder. It's all in a microcomputer. So SDR and Atmel 3200. The reason why we have extras is every student, or at least a partner of a student, has to have one of these in my communications class because we do experiments and problem sets with it. And I tell them, yes, it's going to cost you $150, but if you're that poor, we will buy it back from you or also reimburse you. And if you're not a ham especially, it's not of much use unless you want to listen to hams or get your ham license. We'll buy it back from you. So I have extras of these. They're already built, guaranteed. They're all to spec and everything because they use these in the lab. The interesting thing is I give a talk on this radio because this is the final output transistors, 3 BS170s. You figure, how do they put out 5 watts without a heatsink? Well, this is the unique thing about the USDX radio, if you guys have seen it or studied it. It's a switching RF amplifier, like a switching power supply. It's a switch. It isn't a sine wave and then modulated like regular. It's not linear. It's a switching, but it's interesting how they do it. It's a PhD dissertation done by Andrei Semilak. And I give a talk on this. I try to make it non-mathematical. If you guys are interested, how they achieve 80 to 90% efficient at RF. And in a switcher, you would think, well, if I need 30 megahertz RF, don't I have to switch at 180 megahertz, 10 times that or so? At least 10 times? No, you don't have to. It's pretty tricky how they do it. And I read through his thesis. I was quite amused at it. And then he worked on this with the Northern California QRP Club. And here's the radio. Anyway, I can give a talk on it if you guys like, or if you, I've got like 5 or 6 spare radios. If you guys want to buy it at our cost, guaranteed to work. Comes to the microphone. Again, this is a CWD code, CWN code, has all modes, single sideband. Pretty cool for what it is. And all the filters. Of course, it's all these SDRs. They just write the code for 100 hertz to 4 kilohertz filters. But anyway, yeah, so I give these talks because I need to raise funds. I won't let my students talk, but I'll let them build antennas, and you see the room. They can, and I train them, and then we basically try to cash in on it. So you get, because you're in this talk, you get them at 20% off. The dual band bass that I just talked about is $40. That retails only $55 off our website. The roll-up version of that retails for $60, and you get that for $45. The tri-band, which I didn't give a talk, that actually retails for $95 with shipping. You guys get it for $70. So that's a pretty good deal. And then if you're into GMRS, that gain one, we make a very popular, that gain collinear. We retail that for $65. You guys get it for $45. Oh, and some accessories, the extra cables are $7, and a BNC to 259 adapter for the roll-up to put it to regular radio on, that's $3. So I don't have this on there because if you guys need some, I probably have 4 or 5. I teach this class every other quarter, so maybe half the students don't need them. And I've said, now they're already built, they're ready. I'll give you back the money. Don't worry about it. So I end up with some. It's a really cool. By the way, the battery's built in. It's a 4 ampere-hour lithium-ion battery. It weighs about. It looks like a size of a novel book, like a novel. Weighs about 12 ounces. Pretty light. Comes with a microphone. It's got a little. Doesn't have a wire tuner. The antenna that I like with it is the QRP kits resonant dipole. Yeah. Anyway, I give a talk on it. I think it's one of the newer ideas. It's, Flex Radio is exploring this. It's a very interesting, way to do an amplifier. It isn't perfect because it's a switcher, so the distortion is always about, the way they did it here, 3 to 5%. You would have to sample faster to get it lower, but it's interesting. It works. I make a lot of contacts. I do sodas and podas on. Anyway, okay. I'm open to questions. That's what I'm open to. Open to questions right now. Come up to the mic. Ask me questions. No questions? Okay, I'll ask a question. How many of you guys want to? Oh, question? Go ahead. I heard someone speak.
I think someone was laughing.
What?
You heard laughter.
Yeah, come up to the mic. Just come up to the laptop or wherever it's being displayed. Okay, let me ask a show of hands. How many of you guys are willing to support us? How are the hands, Justin?
There's several hands. Can we do the view from this camera? Is it possible?
Maybe.
Okay, let me get it. Since I don't see the audience, how many of you guys already have one of our antennas?
Yeah, like 2 or 3 hands up.
Okay, tell your friends, support us. We guarantee them, and our antennas work really, really well. I think we put a lot of effort. We simulate them, and a lot of work's gone into them, mainly because my students need things to do in the lab. They need thesis subjects and all of this. So we got good equipment in our lab. We really do good measurements. Oh, there's a group. Wow, that's cool. That's pretty good group. Oh, what kind of hall is that you guys meet in? Looks like a nice place.
Yeah, it's a conference room from a chemical company.
Oh, really? Wow, that's nice of them to give it to you. It's always hard to find a place to meet. And the other one is field day sites are hard to find.
Yeah.
So out of that big audience, come on, give me some questions. So again, now I'm seeing you guys. Raise up your hands again. Who are willing to support buy one or two of our antennas? Good price. Raise your hands. I don't see one. I see 1, 2, 3. Well, spread the word. Once you receive them, spread the word. It's a really good price. Again, when I give a talk, I give 20% off because I just do a club order. I'll send Justin or one of you guys a spreadsheet. You just check them off and then send it back, and then I just do one order. So anyway, it's awesome.
The antennas, were you done you figured out how to do the 440 and then add 220 into it? Was it your students who done this?
No, I came up with the idea.
Okay,
That
so
one
you got to figure it out.
Maybe I should give a talk on it, right? Schedule me in. I'll explain how we did it.
Okay, I was just curious. So you're the one who done all the testing and figured it out.
Oh yeah. Hey,
okay.
my students can barely get their ham licenses. By the way, what my students do is they'll cut all the wires for me and drill holes. I put them all together myself. It is not worth having my students physically build them. Because to build a good antenna, the solder joints and at UHF, VHF, you really have to be experienced. So what I do, they prepare everything for me, but I end up, every single antenna that we've delivered was built by me and tuned by me. Because the good news is in this way, if something doesn't work, it's always my fault. Because a master's student only stays here for 2 years.
I know.
So let's say I screw everything up and they're gone, right? You can't do that. So basically, they cut the pieces. I mean, these like an antenna like this. There's a lot of pieces that go with this. The stubs, cutting this piece, soldering it. Let's see, or let's say here, you don't even see the end cap. There's an end cap here with the drilling the holes, screwing in the connector. There's a lot of pieces that go into this, like these quarter wave stubs, this piece here. So they do all that, right? And if they do it right, then it really makes my job easier, putting it all together and tuning it. That's what they basically do. Yeah, everyone.
You have a catalog of all your antennas and the radios on your website, perhaps?
Yes. They're described, but not the radio, because I don't really sell the radio.
Okay. So on your website, you have a list of all the different antennas you have for sale. And
Absolutely. And then we make any custom ones. You just email me, as long as it's below let's say 500 megahertz. If it's below 500 megahertz, we can make them custom. We can make them single band, dual band, up to tri-band, and that's about it. We do a lot of commercial business. In fact, most of our business is commercial, dollar-wise. But the hams don't hurt. Probably 40% of our business is ham. And we've sold probably over the 20 years about 45,000 of these. It's interesting. I go on trips. You go on trips and you drive down the road. Oh, there's one of my antennas. Hey, there's another one. Down to Texas, to Tennessee, to Chicago. You'll see them all over there. Again, 45,000. There's a lot out there. Our main commercial vendors, ATD Alarms, with their mesh network. You see it. We catch them. And people use these on repeaters. We'll do custom. We don't advertise it. We do a 4-element collinear for UHF repeaters. That seems to be very good when people use it on repeaters, but that's like semi-custom. I'll do it for people, repeaters here and there. If they describe exactly what they need, we'll build them. But yeah, we don't advertise that. So anything custom between 1 to 500 megahertz, depending on the frequency, up to 4 elements. But that, after 4 elements, it's tough. It's point of diminishing returns. You could say, well, if you double that, don't you get 3 dB of gain? Theoretically, you do, but they got to be all phased right. You can, like, we sell the 2-element collinear. In fact, this one here, I'll show it to you. This one I can do 2-element collinear. I can phase this element to this element, phase delay. You can do. But in order to get another 3 dB, the 2-element has to be 4-element. You got to stack 4 of these on top of each other. And you got to do it very carefully because, as you know, if it's out of phase, it'll start canceling. So in order to really experience gain, you got to put together piece by piece and make sure it's in phase. Then you get good gain out of it. And then the other thing that I tell people, it's not all about gain, as you know, right? Actually, we find that these two elements work quite well. When you start getting up, again, you can do 4 elements for a repeater. It seems to be okay. You buy some of these really high gain Sight Masters. They're debatable because they've got 9 dB of gain, and some of them really will give you 9 dB of gain if you're sitting on a hill 150 miles out, right? You can't make energy, so all you can do is reroute it. A 9 dB gain antenna is basically making your spherical pattern into a pancake pattern or flying saucer pattern. So it sprays it further out, but then you shadow people beneath you. And so I try to explain to fire departments and police departments, since you're on a handy talkie, there's no point in having good gain. You want coverage locally, 5-6 miles around you with handy talkie coverage. And that means you don't need 100 watts. You need about 20 watts, if that. You're trying to get coverage to handy talkies. The more power you have, the more you have to isolate your duplexer. You can't hear those handy talkies. Back off. And then you don't want your signal spraying out 120 miles out. You want that energy locally because you're talking to handy talkies. So it's the little things like this that I've learned throughout the years. Not heavily mathematical, but it just makes common sense. Again, high power is not always the best coverage for a repeater because you just desense your receiver. And again, majority of the times you're talking, if you have a 100-watt repeater, you have to ask yourself, so how many other people have 100 watts coming back at you? Not many. So why have 100 watts? It's just that much more. You have to isolate on your duplexer plus the power you have to expend. So little tricks like that. The simple things I've learned over the years. You don't need big mathematical analysis. I'm what you call a very, very practical engineer. That's what everybody says. You're very practical, aren't you? I go, I'm a ham, right? I went through all this stuff. I teach. I'll teach Z transforms, Fourier transforms because you have to, and I try to apply it. Saying the reason why you got to learn this is because of this. But a lot of the others, it's the stuff that if I haven't seen it in 40 years since I graduated from school, more than likely I won't teach it. I won't. Yeah. And a lot of the people I talk to say, I wish I had you as a professor. I go, not always. I mean, there's a fun part to my classes, but we do cover a lot of the math. It's just required. E&M, whenever you're in E&M with Maxwell's equations, sure, you got to cover all the Maxwell's equations and all that stuff. But again, if you explain Maxwell's equation in a very practical way to propagation, then people tend to remember it. Why? Because that's how I remember. I don't remember. When they threw all that stuff at me, boy, you just digest as much as you can to pass the class. You're out of there. Anyway, you guys have still a meeting, right? I am done. If there's any more questions, please help us out. That's how we support our group, and that's how we support Henry. One-man show here. What's this? Did you say something, Justin?
No, one of us said it's a good presentation.
Okay, thank you. So if you want to hear more, just not even if you don't want to hear more. If you're desperate for speakers, because I know how I am. Oh man, sometimes you just can't find people. I've been doing, chairing our clubs for 20, 30 years. You just run out of friends. In fact, they don't want me to call. I start calling them and go, oh, you want a speaker again, huh, Ed? Yes. It's the only time I talk to. But usually I try to buy them dinner or something. Anyway, okay, thank you very much. I'm going to send you a spreadsheet and hopefully you can help us out. That's how we support ourselves. Okay? You guys have
Thank you for your time.
Yeah, you're welcome. Here I go.